Okay, Astronomy 1020, welcome back. We just had a horrible internet glitch where I lost internet. And so the beginning few minutes of this class got destroyed. I may not upload them because we really didn't do anything except kind of, well, actually, I did have some important announcements, so I am going to have to upload them. Basically, we have a new homework assignment today, and we'll get to that eventually. And I'm a little behind on grading last week's homework, but I will get to that. Okay, so let's see if we can salvage some part of this class. We don't have to do everything, but there are a few things that I wanted to be able to get done today. The first is I want to tell you guys about a basic science thing called the Doppler effect. I made reference to it last time when I told you that a spectroscopic binary was based on Doppler shifted spectral lines. And I realized that in our chapter on light and telescopes, I didn't quite get to the Doppler effect, and I wanted to kind of push forward. But this is a good place to introduce it because it's kind of a classic science thing. People use it in many different applications of science, but especially in astronomy. First of all, I would like to remind you guys that studying binary stars in astronomy has a point. I wonder if you guys remember what the point is. What is the point, or what is the usefulness of studying a binary star system? I could see how this may have sort of slipped through the cracks during our lecture last time. What is the point of... Oh, Christopher?
Is it because like a lot of them are like a lot of the stars we see are binary systems?
Okay, so a lot of the stars we see are binary systems. That's good for us, but the binary stars give us something that you cannot get from other stellar studies. And it has to do with this HR diagram here, function F5. It has to do with the fundamental properties of stars. Let's see what's going on in the chat log here. Oh, it's just LOLs. Okay, that's not helpful. Look, what's the point of a binary? No one knows? I'll give you a hint. It's to discover one of the fundamental properties of stars. What are the fundamental properties of stars? I know you guys know this much.
Oh, it gives us luminosity, right?
Not luminosity.
Radius, temperature.
Nope. You can get those things directly off the HR diagram. You get temperature from the spectrum. You get luminosity from the y-axis. Okay, fine. You guys don't know. It's the mass. And that's kind of why I'm repeating this point, because I expected you guys to forget this. The point of a binary star system is to find the mass of the two stars. And you guys actually did this in one of your labs. As one day Austin pointed out to us, mass is the most fundamentally important property of a star because a star is a big fat ball of gravity. And that ball of gravity is squeezing in on itself until nuclear reactions kick in the core. And then you have a beautiful glowing plasma ball in the sky. And then the stars twinkle at night and you feel happy, okay? So these are things that matter to us. If we care about the twinkling stars in the sky, stars determining their mass will determine how long they can undergo fusion. I got a little carried away there. Anyways, the way you find the mass of a binary star is you use the observable properties of a binary so that you can plug them into Newton's version of Kepler's third law, right? So in fact, I want to just say one more thing. Now I remember what I was forgetting. Let's look at the HR diagram together. If you guys look up close along the main sequence, you will see a tight correlation between the mass of a star and its spectral type, but only along this diagonal called the main sequence. Let's zoom in on the main sequence here together so you can get a better look at it. Stars like Proxima Centauri are little teeny M-class stars. They're these very low temperature stars with low masses, somewhere around 1/10 of a solar mass. And the spectral type O stars they can go up to 100 solar masses, and these are the big bright blue stars that make the spiral arms of galaxies blue. But stars only fall along this line when they're in the first stage of their life, where they are fusing hydrogen into helium. At later points in their life, they will expand and become red giants or maybe even blue supergiants. And once they've left the main sequence, we really don't know what their masses are unless we can find them in a binary pair. And as a dramatic example of this, let's take one of the most famous and fun stars in the entire sky, that big fat red giant Betelgeuse in the upper left shoulder of Orion. Betelgeuse is an interesting star to us because we believe it's on the verge of going supernova and will one day make a pretty cool cosmic light show in our sky. But Betelgeuse is famously a singleton. You know what I mean by that, right?
It's a single star.
Exactly. It's not part of a binary pair. And I want to show you something on the Betelgeuse Wikipedia page. Because Betelgeuse is a singleton and it's not part of a binary pair, and because it's not in the main sequence, we really don't have a good idea of what its mass is. It looks like it's actually been updated since the last time I looked at it. We believe this is definitely a new study here. Can I? Oh, Control Plus. I just want to zoom in on this so you guys can see it a little better. According to some study which they've referenced here oh wow, this is from this year. Standing on the shoulders of giants, new mass and distance estimates from Betelgeuse. Wow, that's really cool. So this was just published this year. But look at the mass range on Betelgeuse. It's still between 16.5 to 19 solar mass units. In other words, it's somewhere between 15 and 20 solar masses. The uncertainty on its mass estimate is really terrible because we don't have a binary star to accurately measure its mass. All of this was just me trying to remind you what the point of a binary star was. The point of a binary star system is you want to use it to find the masses of two stars. You do that, of course, with NK3, the Kitty edition. I'm telling you this because binaries are going to be a big part of your final exam this year, so I'm trying to warn you in advance. We're going to find the total mass of the two stars with a very simple formula, a cubed over p squared. Okay, students, this is your time to shine. Do you remember the units for the Kitty edition of Newton's version of Kepler's third law? What are the units? Enlighten me. Oh dear, we are so screwed. We are so screwed. No one can remember the Kitty edition units? Maybe somewhere in your notes? It's not MKS units, Christopher. That's the point. MKS units make the problem really hard. The Kitty edition makes the problem easy because it's not MKS units.
AU?
That's right, Austin. A is measured in AU. How about the period? You can think of them as Keplerian units. Years, says Kaitlyn correctly. Thank you, Kaitlyn. Years. And the masses.
Kilogram?
No, it's not MKS.
Isn't it solar mass?
Exactly, Arunsak. That's what we want. Solar mass units. Can't be meters, Kaitlyn, because it's a mass, right? Okay. I think you realized that after you said that, right? Okay. All right, cool. So solar mass units. The problem is when you study a binary star, getting the period is always easy. You just wait for the binary star to sort of revolve or do some periodic cycle, and you can usually directly observe the period. But getting the A is a little bit more difficult. However, it's possible to get A by measuring the velocities of the stars. And this is where the Doppler shift is going to come in. Now, I think I walked you through this argument in a homework once, but maybe it's a good idea to go through it again. So the next point that I want to make, I'm kind of building a little tree for it here. So each platform depends upon understanding the one below it. So the next key idea is you can get A, which of course is the separation distance. You can get A, the separation distance, by measuring the velocity. And astronomers do this all the time, not only in optical astronomy, but also especially in infrared and in radio astronomy, by measuring the velocity. And the idea goes something like this. The idea goes, if one of your stars is the more massive one, and the other star is the kind of less massive one, then for the most part, it kind of seems like a planet orbiting a star or a moon orbiting a planet. It's kind of going around in a circular orbit in which the radius of orbit is A, the separation distance between the two stars. And as I mentioned once before, the circumference of your circular orbit is 2 pi A. And if it travels this distance, you can use the formula distance equals rate times time to write down this important formula. You can say the distance is the circumference, 2 pi A, and distance will be traveled at some velocity in some unit of time, which will be the period, because you're traveling exactly around the circle once. And you can always measure the period. You want the A. So you can solve for A using the so-called binary star formula. A equals V times P over 2 pi. And believe it or not, I've actually, can I angle the camera slightly up? Is that better, Cam? You like that? Perfect. Okay, cool. This binary star formula, A equals velocity times period over 2 pi, you've already used this once in your homework. And here's a secret. You're going to do it again on your final exam. Okay, that's why we're drilling this in, to make sure that it's not a surprise to you. If I can measure the velocity, I can get A. And this is the secret behind a spectroscopic binary. We can get velocity from the Doppler effect. This is what I wanted to start off today talking about. Cam and people who are taking notes, can I erase this? Does anyone need a second? Okay. I'm going to move kind of quick today. I got a lot to cover. So after a long setup here, like this was a kind of big elaborate setup, I can finally explain my motivation of why the Doppler effect is so important. And the idea is you get the velocity from the Doppler shift, or the Doppler effect. The Doppler effect is a key idea in science. So it's bigger than just this astronomy class. It's about becoming a scientifically educated person, okay? And the Doppler effect, let's see if we can define this. They sometimes refer to it as the Doppler shift. And it's a phenomenon that occurs with almost all types of waves, but particularly with light waves and particularly with audio waves. The Doppler shift is a shift in either wavelength or frequency due to the motion of a moving object. And it could be the shift in wavelength or frequency of a light wave or a sound wave. Those are the two most common phenomenon. It could be a light wave or a sound wave. And you've probably heard this if you've ever heard an ambulance race by you on the street corner. You know, living in downtown Providence, there's constantly mayhem. One of the reasons I like living down here. And there's always police cars scrambling by or sirens going off. And if you stand on a busy street corner and a siren goes past you, you can actually detect the Doppler shift with your ear. If you think about it, the police cruiser has a siren that's going, woo, woo, woo. And when the ambulance races towards you on the street, you can detect an increase in pitch as the ambulance goes, woo. And then as it passes by on the street, it goes, woo. You can hear the change in the frequency. Let's look at a little screenshot of what's going on here. I didn't get really great images for this in my slideshow, although I should look again because there's probably better ones now. But I have a little tidbit in my light lesson. I also have a demo on the Doppler effect that might be fun. So this is, I think I want to draw this instead because I don't like that picture there. So let's try to look at how the Doppler shift works with a star. Okay, let's say that you have a star. Let's make this a cheesy star that is a green star. As you guys know, there is no such thing as a green star, but we're just going to pretend for a second. And you, the observer, are over here on Earth, and this green star is emitting green light, which has a wavelength of around 500 nanometers. If the star has a motion towards the observer, so the motion is along the line of sight, as the star emits successive wavefronts of green light, the star will start to barrel into the wavelengths of green light, and it will smush and compress them. And as it compresses those wavefronts, they will get a shorter wavelength, and they will become so-called blue shifted, okay? So the idea behind a blue shift is that a blue shift happens when the star has motion toward the observer. I'm going to try to keep this simple here. Motion towards the observer, and it causes the wavelength of light emitted to become shorter. So this results in a shorter wavelength of light. It's a shift towards shorter wavelengths. Conversely, if my green star moves away from the observer, so here it's you, the observer, and here's my green star. This time, it's moving along a line of sight away from the observer. What start off as 500 nanometer wavefronts become pulled apart or stretched out as the star travels away from each successive wavefront that is emitted. The result is that the light undergoes a red shift and the wavelengths become stretched out. So a red shift, let's see if I can angle this camera a little bit down here. A red shift is when you have motion away from the observer. And that usually means you have a longer wavelength of light. Can you guys read that? That wasn't spelled out very, very well. These shorter and longer wavelengths have an analogy in sound as well. A shorter wavelength sound results in a higher pitch. So when the siren moves towards you, you can hear the siren go whoop. And when the siren's passing by you and the wavelengths get stretched out, that's a lower pitch. Woo. It's important to realize that because stars mostly give off absorption line spectra, the blue shift and the red shift don't often take the form of an extreme shift towards the blue or towards the red, but often just result in a slightly, let's see here, Shoot, I forgot what slide that was. I'm doing this badly today. Where are you? There we go, 92. So function F5, 92. So let's talk about the middle spectrum here. This could be the spectrum of a star, and we see a very famous absorption line. I don't suppose you guys know what that double yellow line is, do you? Can you guys identify the element there that they're referring to? Maybe this is too much.
Is it some sort of hydrogen?
Hydrogen is over here. This would be the hydrogen alpha line. But the double yellow line is from a famous element. Sorry, Cam, not helium. It's sodium. This is the sodium doublet. Sometimes I tell students about the sodium doublet when we're studying emission lines and absorption lines, but maybe I didn't tell you guys about that. Okay. So notice, if you will, that the sodium doublet, we could do it with the okay, since you guys recognize hydrogen, let's talk about the hydrogen alpha line. Notice that when the hydrogen alpha line becomes redshifted, first of all, it's already red, but you see the wavelength just gets a tiny bit longer. And when the star moves towards you, the blue shift results in the absorption line just getting a tiny bit shorter. So a blue shift and a red shift doesn't mean that the light turns blue or turns red. It just means that there's a small increase or decrease in the wavelength of light. Okay, pause for 1 second. Okay, I want to see if I can do a little demonstration showing you guys how this works. And then we're going to see the formula for the Doppler shift. So this is usually a little more fun when we do it in class. But I have here a little handmade piezo buzzer. It's not very loud, unfortunately, because I think I wrapped too much tape around the speaker, but tell me if you guys can hear this. Can you hear that? Okay. So this is just a stupid buzzer that emits a very, very irritating and annoying tone. And according to this thing, last time I looked at it, I think it's right around 300 hertz. And that sound is one of the purest elements of sound. It's just a perfect sine wave. It just sounds like, ooh, oh, I just scared the hell out of your cat. Awesome. All right, well, this is really going to scare the hell out of your cat. What we're going to do is I've got it attached to this rope here, okay? And what I'm going to do is I'm going to activate the buzzer. Wait, can you guys still hear it if I stand back here? Can you hear that? Okay, cool. All right, so this microphone's a little more sensitive than I thought. So what I'm going to do is I'm going to attempt to create, I like pad thai. Austin, I love Thai food, but my favorite Thai food dish, if you really want to know, is a special dish called pad gra pao. And you can't just get this at any Thai food restaurant. It's Thai holy basil. We can talk about that sometime. Anyways, okay. Yes, you want to know about this. I learned about it in grad school from Andrei Solokov, the Russian graduate student who was a good friend to me and helped me in many jams. And he taught me about this dish, and it's wonderful. Anyways,
a real good guy.
He's a good guy, yeah. So listen, we're going to try to recreate the Doppler effect here. I'm going to create this pure tone at 300 hertz. It's going to sound like this, ooh, and I'm going to start to swing it around, and we're going to see if we can create a Doppler effect. But do you guys know, can you predict, let's use like our science intuition here. What do you think it's going to sound like if I swing this thing around in a circle towards and away from the observer?
Higher pitched and then like lower pitched as it goes away.
That's right, because what's happening, Austin, is when it moves towards the observer, you should get a blue shift, and you should hear a short wavelength and a high pitch. When it moves away from you, you'll get the red shift and the longer pitch. But here's the thing: it only works towards and away from the line of sight. So at those moments where it's moving perpendicular to the line of, so you guys understand what I mean about motion along the line of sight, right? Like if you guys are the telescope, this is towards the observer And this is away from the observer. This is along the line of sight, right? But this is perpendicular to the line of sight. When the thing moves perpendicular to the line of sight, you will get no Doppler shift, and it'll go back to 300 hertz. So Austin pretty much had it right. You'll hear the high pitch, the low pitch, and it will oscillate. Let's see if we can do it. Can you guys hear that? It usually works pretty well in the classroom, but this thing sounded kind of quiet to me. Could you guys hear the changing, the warbling of the pitch? Okay, cool, right. So you guys have, the point that I'm trying to make is the Doppler shift is not some super mystery of science. This is something you've probably heard before or experienced in your lifetime. The point is astronomers depend upon it to measure the velocities of stars. I think I was right about here. Okay, now it's time for you guys to learn the formula, okay? Okay, let's assume that we have some rest wavelength. And that rest wavelength is an absorption line feature, something like hydrogen alpha. Hydrogen alpha, when it's at rest, has a rest wavelength of 656.3 nanometers. During the Doppler effect, it can experience, so we'll say that wavelength increases to the right here, okay? It can experience a red shift or a blue shift, a longer or a shorter wavelength. This will be the red shifted wavelength. And although it'll still be red, I'm just going to draw it here. This will be the, actually, you know what? I'm going to make a point here. I'll use orange for the blue shift, okay? Now, there is the original wavelength, and then there is a new wavelength called the observed wavelength, okay? So lambda rest is the original wavelength, and lambda with no subscript is the Doppler shifted wavelength. And if I subtract the two to get the difference, this is what is commonly referred to as the Doppler shift. It's lambda minus lambda rest. And the Doppler shift, the change in wavelength, is related to the velocity by the following formula. The velocity of the star can be computed by multiplying the speed of light times the change in wavelength divided by the rest wavelength. And although this might seem a little confusing, from my point of view, I think it's a very logical formula. It just tells you that if your change in wavelength is, say, 1% of your rest wavelength, then your velocity will be 1% the speed of light. If you change by 2% of your rest wavelength, your velocity will be 2% the speed of light. So whatever your percent shift is, that's the star's percentage of the speed of light. Obviously, most Doppler shifts, because stars travel much slower than the speed of light, most Doppler shifts are tiny, microscopic little shifts in wavelength. So usually what happens when you're studying a spectroscopic binary, wow, I've wasted a lot of this class on this idea, but what the hell, I decided today that I was going to do it right. So this is, also we're going to have a homework problem today on it. This is the concept behind how a spectroscopic binary works. 101. You are here, you're the observer, okay? And two stars are orbiting around each other. The little star moves towards the observer and away from the observer. And what you can see happening is the rest wavelength is in the center, And as the stars move towards and away from the observer, you see two sets of Doppler shifted absorption lines. The goal of the astronomer is to measure the Doppler shift, then calculate the velocity, then calculate the separation, and then calculate the mass, which is what you really want, okay? This formula will be used in our homeworks today. So I'm not going to do a sample problem on it because I've spent a little too long on this topic today, but there you have it. Does everyone have this down? Okay. So that part of today's lecture was a little bit technical. The Doppler effect is a technical concept in science, but I thought you guys ought to learn about it because it's used in so many different applications in life. Like if you get a speeding ticket and that police officer is shooting his laser gun at you, what do you think he's using to measure your speed in the car to tell you that you were going 95 in a 65-mile-an-hour zone? He's bouncing a laser off of your car. He's using the Doppler shift to calculate. I mean, he's not really doing it. You know, they don't, I don't know. Anyway, so someone's doing it. A computer's doing it, okay? Anyways, this is an important concept. We use it all the time in astronomy. All right, let's change topics for a little bit. We're going to take a look at the places in our universe where stars form. And that thing is called the interstellar medium. This is the stuff that I really wanted to get to today, but I kind of got carried away with the Doppler effect there. Here's a picture of some cool gases in space. I believe this is the Eagle Nebula. And it's important for you guys to realize that in between stars, there is a tremendous quantity of gas. This gas is the material that stars form from. And as we saw in our last week's homework, this stuff is the material that you form from too. We calculated in our last homework that the water molecules that make up your body were once dispersed across these so-called giant molecular clouds. That's the name of these beautiful dark finger-like structures. Some of them are so beautiful that they have famous names. This structure here is known to astronomers as the fairy, and these structures here are iconic. They're known as the pillars of creation. And these things are super long. Like one of these structures could easily be up to 100 light years long and contain thousands, maybe even hundreds of thousands of solar masses worth of material. Someone asked me.
What's the first one called?
The fairy. And both of these structures are in the Eagle Nebula, which is what this is. So if you Wikipedia Eagle Nebula, you should see something like this pop up. I also want to show you another cool picture from space. I just want to show you a picture of a famous galaxy called the Sombrero Galaxy. And if you've never seen it, it's pretty beautiful and awesome to look at. Let's see if we can get a Wikipedia picture of it. Sombrero. Here we go. There's an iconic photograph of this galaxy. This is a real picture. This is not space art. This is an actual photograph of a galaxy. It's known as the Sombrero Galaxy because, well, it looks kind of like a sombrero. One of the reasons I like to show it to students is to remind students that there is a tremendous amount of gas in the disks of galaxies. We're used to thinking about stars, but in between stars, if you look at an entire galaxy, you see tremendous quantities of gas. And this gas is the interstellar medium, okay? Kaitlyn, we saw you giving some love to your cat there. All right. Anyways, let's learn about the interstellar medium. This is where stars are formed. A astronomers love acronyms, and they refer to the interstellar medium as the ISM. And we can define it as the gas and dust that exists between the stars, almost always in galaxies. Most people believe that the density of matter in between galaxies is very, very low and hardly anything at all in comparison. So the gas and dust that exists between the stars and galaxies, from which stars and planets and in a sense, and you form. So the chemical composition of the interstellar medium is directly related to the abundances of elements that we find on Earth. And in general, the composition of the interstellar medium is a lot like the sun, obviously because the sun formed from it, but there are some very important nuances I want to talk about today. So first, we have 70% in the form of hydrogen gas. And the hydrogen gas actually takes 3 different forms, but I'm going to come back to that later. I just want you to know that not all hydrogen gas is the same. Then 28% of the interstellar medium is in the form of helium gas. And you guys remember what we called the remaining 2% elements of the sun, right? What do we recall? What do we call them? I'm having a hard time speaking today. It's not, words aren't coming out. Heavy metals, that's right, Cam. Okay, cool. So they're called metals. Here we're going to differentiate the 2% heavy metals. 1% will be in the form of atomic gas metals. And I'm using metals in the astronomer term. An atomic gas metal could just be a carbon atom. It could be a nitrogen atom. It could be, who knows, an iron atom, just floating in the void of space. But the idea is it's in the form of gas. The remaining 1% is something different. That remaining 1% is in the form of solid grains called dust. Now, dust is kind of a big deal in astronomy. Dust are metals that are in the form of solid grains. Now, first of all, we need to differentiate between dust and dust. I ain't talking that windowsill dust. I ain't talking the dust bunnies under your bed dust. What's the dust on your windowsill made out of? Does anyone know where that dust comes from?
Isn't it just like particles?
Particles of
The ground.
Of
dead
cat
skin.
hair, things.
Yeah, hair it can be part of it, but normally those dust motes that you see are like sloughed off skin cells. And I know it's kind of gross. You can actually see those motes of dust with your eye. The dust grains in space are much smaller than that, and they're obviously not made of sloughed off alien skin cells. They're made of tiny bits of carbon and silicon. So I need to teach you guys about in fact, there's a name for it. Astronomers refer to this dust. Well, space dust is okay, Cameron, but they call it cosmic nanodust, which is also kind of cool. So it's called, in fact, guys, can I erase this and start up at the top? Because I have a lot to say about dust, believe it or not. I kid you not, I have a lot to say about dust. I'm erasing this. I have some pictures to show you as well. So let's talk about cosmic nanodust. Now, the reason why I'm telling you so much about nanodust is, in a way, the material of Earth and the material of your bodies is made from cosmic nanodust. But cosmic nanodust also plays a huge role in star formation and many other areas of astronomy. A picture could be helpful here. A scanning electron microscope of a particle of cosmic nanodust might look something like this, slide 9. This is a solid grain, but at 100 nanometers across, this is too small for your eyeballs to see. A typical construction of it would be mostly something in the form of carbon with pieces of silicon in it, and sometimes even an ice coating. But for the most part, when we think about cosmic nanodust, we're going to think about the element carbon. Let's make a model. The composition is carbon primarily, sometimes silicon, sometimes ice. Usually the length is typically around 100 to 300 nanometers. The book reminds us that you cannot see something of that size. It's more like a particle of smoke than it is like a dust grain on your windowsill. So they sometimes have oblong shapes, okay? So this is carbon. There might be chunks of silicon inside. And I'll give you some examples of what this stuff is. So this could be bits of silicon. And there could even be a little sheath of ice around it, something like that. Do you guys know what the two forms carbon takes in nature when you have a pure lump of carbon? By the way, we refer to these as allotropes. Go ahead, Austin.
Is it carbon-6?
Well, I am talking about mostly, so Cameron knows one of them. Graphite is one of the allotropes of carbon. Do you know what the other one is, Cam? No. Well, silicon's a different element. I think it's time we took a little trip to Wikipedia and we learned about the allotropes of carbon. I kid you not, the allotropes of carbon is one of my favorite Wikipedia pages. And you just don't anticipate how interesting carbon is. Allotropes of carbon. Okay. Here we go. So it turns out that there are several different allotropes of carbon, but two of the more famous ones are diamond and graphite. So let me just slide down here. Actually, carbon, when it's kind of lumped in space, is actually, you might think of it as like a lump of coal. I usually have a lump of coal to pass around. I have a piece of what I think is anthracite. It's one of the types of coals that I found in a coal bin when I was exploring this house one day. And coal is kind of dark and black and sooty. And this is what carbon usually takes the form of in outer space. But I just goofed up there. The two main allotropes of carbon are shown here. On the left is diamond, and on the right is graphite or pencil lead. Now, what makes these two allotropes different? They're both made entirely of pure carbon, but in the case of graphite, the carbons are arranged in these hexagonal structures, which are then spread into these long, long sheets. And this is why you can use a pencil to make black, dark stains on a paper, because when you drag the graphite across paper, you are literally tearing off these carbon sheets, sheet by sheet at the molecular level, and you are staining the paper black. If you compress the hell out of carbon under geological forces, a shift can take place where the carbon atoms rearrange themselves into something called a tetrahedronal shape. Now, what I think is important for you guys, especially if you haven't learned too much about chemistry, is to realize that the same pure element, carbon, once it is compressed, can take on a completely different form. And just by rearranging the positions of the atoms, you suddenly have this beautiful diamond. Although, to be honest, what makes natural diamonds so beautiful is usually 1 out of every 6,000 carbon atoms is replaced with a single strontium atom. And it's that one strontium atom out of 6,000 carbons that gives diamonds all of their shiny and sparkly reflective properties. A diamond, a synthetic diamond made from pure carbon, is actually kind of ugly. So this is an important lesson about life. It's the impurities, it's the weirdnesses that give things their beauty, okay? So in any case, probably most of the dust grains we find in space are going to have the form of graphite. Usually you have to put a lot of compression. However, we have detected the signatures of diamond inside the highly compressed surfaces of white dwarfs. So there may be time to talk about that. But I thought it would be cool for you guys to know about one of the basic building blocks of nature. Carbon is one of the most abundant elements in outer space. How about silicon? Can you think of something made of pure silicon? What form would that take in nature? Okay, well, let's learn some stuff. How about, oh, let's see what the chat says. Those little stupid beads. Maybe that come in a little package. Oh, I see, for absorbing moisture when you ship electronics. Yeah, those are. Plastic, not so much. I think the perfect thing to think about are grains of beach sand. If you think about it, beach sand is kind of like some leftover cosmic nanodust that's, you know, basically found its way to the surface of Earth. Let's see if we can get a nice, cool close-up picture of grains of beach sand. This one isn't too bad here. You'll notice, oh, I hate using these stock photos. Here we go. I like this one. So you guys will notice that grains of beach sand, if you've ever held them in your hands while you're sitting at the beach, they have this kind of waxy like nature to them, kind of like a waxy translucence. Beach sand is almost 100% made out of silicon. And once you melt it down, of course, you get glass. Glass is another example of silicon. People use silicon in industrial applications because it's a semiconductor. And under some conditions, it can conduct electricity or not. So you can use silicon as switches to turn things on and off. But I digress. Silicon is another very abundant element out there in outer space. Okay, so why do we care so much about dust grains? For a bunch of reasons. These dust grains play a huge role in the evolutions of stars. And they also have two effects on starlight. And I want to start by showing you guys a famous structure that people used to observe or still observe. They sometimes call them dark nebulae, or they call them Bach globules. And the first time you see one of these things, it sort of looks like there's a hole in outer space. If you look closely, you'll start to realize that along the edge of the hole are a whole bunch of reddened stars, stars that are redder than their counterparts, which seems like a bit of a coincidence that all of the red stars would kind of line up along the edge of this structure here. It starts to make you wonder if maybe this isn't a hole in space, but this is a foreground cloud that is blocking the starlight that's behind it. Let's take some notes on the two effects that dust has on starlight. They're going to play a role in many areas of our class. Okay. So two effects of dust on starlight. The first effect is called extinction. And extinction is when grains of dust block basically all types of wavelengths of light. So for extinction, dust blocks all wavelengths of light. This is important because it's responsible for a lot of the dark dust lanes that we see when we look at galaxies. However, dust does not block all wavelengths of light equally. It selectively blocks blue wavelengths more than red wavelengths. And this is what is known as reddening. In reddening, dust blocks or sometimes scatters blue wavelengths more than red wavelengths, okay? This whole lecture has been a blue versus red thing. I don't know, it kind of reminds me of this election results we're waiting on. All right, so in any case, the dust grains look something like this. Let's draw a little cartoon, okay? So here are these dust grains. And let's imagine some photons are trying to propagate through the dust grains. This is going to be one of your homework problems today that you're going to work on with me. And we'll get to taking a break soon enough. Because red wavelengths are longer, they can kind of wiggle their way through the dust grains without, by the way, the reddening that you see in those wildfires, Christopher, is very much analogous. It's related to this process, although it's a little bit different. The optics gets complicated. There are different scattering regimes, but I don't want to get into that just yet. With red wavelengths of light, because they're longer wavelength, they can kind of wiggle their way through the dust without hitting as many grains. Whereas the shorter blue wavelengths of light, because they have shorter wavelengths, they more frequently bump into the dust grains and they end up getting scattered kind of sideways or out of the field of view. This is very similar to what happens when the sky scatters blue wavelengths of light, except it's a slightly different wavelength dependency for well, actually, yeah. The outer space scattering is a little bit different than the sky scattering. But I want to show you how this results in some really cool pictures in space. You guys will remember that last time I taught you about this famous star cluster called the Pleiades. You can actually see the Pleiades at night. Do you guys see how surrounding function F588? Surrounding these blue stars, you can see these hazy clouds of blue. All of that cool blue gas that you're seeing is scattered blue light from dust grains in the interstellar medium that surrounds the stars. So what's happening here, these are called reflection nebula. They're very beautiful. At first, the blue photons leave the star, then they hit a dust grain and pow, they scatter towards the line of sight of the observer, allowing you to see some of these blue grains. There's a couple of famous, they call them reflection nebula, and I'd like to show you a few pictures of them. Reflection nebula can be some of the most beautiful types of nebulae to look at in space. Reflection. If we just type reflection nebula into our image search, ooh, this one is very appropriate for Halloween here. This is the so-called Witch Nebula, okay? The Witch Nebula is a beautiful example of reflection nebula. Anytime you see these cool blue clouds of gas in space, usually it's an example of dust grains scattering blue light. I don't know. Let's try the Trifid Nebula. Sometimes you get an emission nebula and a reflection nebula together. The Trifid is one such example. That's a pretty nice image. So if you guys can see all the blue light there, that's all blue light from scattering from dust grains. So dust grains are responsible for this. Now, let's see what you guys remember. Do you guys remember what's responsible for the red color that you see here? The so-called emission nebula? Who knows what that is? Damn, and I thought you guys were cool. I thought you guys knew about cool stuff in space, but now I see you're just ordinary people who just don't know about nothing. You don't remember what happens with the red emission nebula? No? We learned about this in one of our lectures. It's hydrogen alpha. That's hydrogen gas, right? The 3-to-2 transition of hydrogen? No. Oh boy. Okay. Well, look, I want to tell you guys about cool things in space, right? But if this isn't going to make an impression on you, then I'm not sure what is. Okay. So look, from now on, you are going to learn these two things from me. There are two types of nebulae that you see in space that are pretty and nice to look at. The red ones are called emission nebula, okay? And they're caused by hydrogen gas. Those are emission nebula. And the blue nebulae are called reflection nebulae, and they are caused by dust grains, okay? So it's a totally different physical process. The blue nebula are from scattering of dust grains. The emission nebula are from heated up hydrogen gas emitting a particular red wavelength of light. And now I've achieved one of my personal goals, which is to teach the class about these two types of nebulae. Okay, let's see if you guys can make a prediction here. If I show you that Bach globule again, function F512, you can see both effects of dust happening right here. At the center of the cloud is extinction, where no wavelengths of light can pass through. And here along the edges, the stars have become reddened. Does anyone sort of intuitively understand why the stars are red along the edge of the cloud?
It has to do something with the wavelength of the red, right?
Well, it has to do with the thickness of the cloud, right? Like, let's say the cloud is a sphere, like rainbow ball here. If you cut through the center of the cloud, you're going to get the maximum amount of extinction because you're passing through a bigger column of gas. But if you slice through the edge of the cloud, you're just kind of skimming the edge of the cloud, and you're not going through as big of a column density of gas. So there, some of the red photons can actually wiggle their way through. Here, the dust is so thick that all the wavelengths get blocked, but it's thinner along the edge of the cloud, allowing some red wavelengths to pass through. So this is the reddening. What would happen if I used an infrared telescope and I looked at this same dark nebula with an infrared telescope? Can you guys predict what it would look like if I took a photo at infrared wavelengths? What would I see?
Yeah, you would see like redder around the edges, but completely black in the middle, right? Where it is thicker.
Kaitlyn says you'd see more red stars. So those are two different hypotheses here. One is, okay, but Kaitlyn, let's start with Kaitlyn's thing. So remember, at infrared wavelengths, you're not really seeing red versus blue, but you can see stars at infrared wavelengths, right? So Kaitlyn, I guess I want to know, where am I going to see the stars?
Would you see more stars that are like behind the cloud if you did it within an infrared thing?
Let's find out. Exactly so. Right? Nicely done. Okay. And that's because, yeah, there you go. You had a good one, right? Okay, so I like that. Now, my hope is that your logic went like this, Kaitlyn. Mega mind answer. I like it. Because the infrared wavelengths are even longer wavelength than red wavelengths. Hey, Elijah, I'm just noticing your cute pooch over there. Let's hear about this guy. Is that a dog or a cat? I really can't see. What do you got there?
This hang on, this is my mom's dog Phoebe, and she's a monster.
Oh, she's a pretty cool looking monster.
my
I'm digging
God.
those black patches on her eyes.
Yeah,
That's
she's
awesome.
she's I don't know how old I know nothing about her. She just
Hey, I'm glad you're hanging out with us today, because normally you're in the night crew, right?
Yeah, no, I managed to wake up before like noon.
Okay, that's hard for me too, actually. I tend to,
hard
you
getting
know,
to-
astronomers stay up all night. They don't really, daytime isn't their thing. Anyways, cool. Well, I'm glad you're here with us anyways. Now let me see if I can unpin you. Remove pin. Okay, there we go. Okay. Dust does other things besides blocking light, but I want to show you guys even, you know, we should probably stop soon. Where am I here? I'm 12:48. Kaitlyn's like, yes, please. I want to show you guys one last, I know that's a very cute dog. I want to show you guys one last picture, okay? And then we'll leave the dust thing behind for now. Dust, we're not done with dust, okay? We're coming back to dust. But let me show you guys a picture of the Milky Way galaxy. It turns out that when you look at cool pictures in space, all of the beauty of a picture like this comes from the absorption of dust. Let's take, for instance, the pillars of creation, which I showed you earlier. The pillars of creation. An iconic Hubble Space Telescope image of molecular clouds in the Eagle Nebula. Once you learn about cosmic dust, you realize that the whole reason this picture looks so badass, you think that you're looking at the gas, the hydrogen and the helium, and for sure the hydrogen and the helium is there. But the whole reason you can see this cloud and the whole reason it looks so beautiful is because of dust grains. That's all blockage of light from dust grains. Now, I want to show you guys a picture of the Milky Way galaxy in the optical band, meaning the visible band. And I want to get a high-res image of that. Can you guys tell me what's going on here? What am I seeing?
A lot of dust.
That's right. That's what I wanted to hear, Austin. These are the so-called dust lanes. And this is why some people say astronomy at optical wavelengths sucks. You can't see anything in it because of all the dust that blocks your view. But can you see what the light is doing here? Can you see what this is? This is just like the Sombrero galaxy. There's the bulge, and there's the disk of the Milky Way. In this image, you can even see the large and small Magellanic clouds surrounding the Milky Way. This was taken by doing a panorama photograph of the entire sky. You know, you could take this picture yourself with a DSLR camera. You just need to go to a dark sky and have a good tripod, and you could totally take this picture. In fact, people make a cottage industry out of taking cool shots of the Milky Way over some kind of backdrop, like their backyard or a famous telescope or something. Like here's someone taking it in probably, I don't know, Aruba or something, right? And they're taking pictures of the Milky Way galaxy. This is splash. Oh, look, this is kind of cool, right? This is a dude staring up at the Milky Way. Some cosmic shit going on there. Okay, anyways, so the point that I'm trying to make is what makes our galaxy difficult to observe are these dust lanes. This is why if you want to take an image of the supermassive black hole at the center of the galaxy, you can't use optical photographs because the dust will block your view. When they took those images of that supermassive black hole at the center of M87, they used radio wavelengths because radio wavelengths are so long wavelength, they can penetrate through all of the dust and they can see the center of the galaxy. People who study galaxies love infrared telescopes and they love radio telescopes because they can see through the obscuring dust lanes and find out the secrets at the heart of galaxies. All right, that's enough yapping for one day. We're going to come back to effects of dust next time, and we'll learn about nuclear fusion. I've got a short homework for us with 4 problems, okay? And we'll take a little 15, 20-minute break and start around 1:10. Does that sound good to everyone? Y'all like that? I like that too. Okay. So we'll take a pause, and I'll see you guys in a little bit. Hey, everyone. What do you say we do this to this while we can? Oh, cool. You're here. Arunsak, glad to see you. Let's get this homework started. There's only 4 problems to do. We can crank them out and then go back to feverishly hitting refresh on election results, or at least that's what I'm going to do. Let's see here. Name AS1020, whatever your section is. This is homework number 9. It's a special homework with 4 problems from several different chapters. Let's see if I wrote them down somewhere. There was one from chapter 15. Sorry. One from chapter 5. One from chapter 15. And 2 from chapter 16. But I don't remember. Let me see here. Oh, this is annoying. Okay. 61, 58, and then 53 and 54. Because 53 is such a long problem, I decided to just give us 4 problems today. All right, so let's go over to chapter 5, number 61. This is a problem on the Doppler effect. And I thought it might be nice for us to do that as a kind of practice problem so that we can sort of see how it might work on a test. We're just going to calculate the velocities of a few stars from their Doppler shifts. Let's share screen here. Let's go over to Blackboard. Sorry. Chapter 5, part 2 ought to get us there. And I'll start us off today. The Doppler calculations. In hydrogen, the transition from level 2 to level 1 has a rest wavelength of 121.6 nanometers. This is the so-called Lyman alpha transition. What type of photon is that, class? And what band of the electromagnetic spectrum is 121.6 nanometers?
Ultraviolet.
Very good, Arunsak. It's known as Lyman alpha. Find the speed and direction of a star in which this line appears instead at the new wavelength, and they give us A, B, C, and D. So why don't we start by writing down 121.6, okay? This is known as the Lyman alpha, or 2-to-1 transition of hydrogen. It has a rest wavelength of 121.6 nanometers. And our goal, the mission, is to find the velocity of the star which is found by the Doppler effect formula. The velocity of the star is the speed of light times the change in wavelength divided by the rest wavelength. Okay, so question A, we have an observed wavelength of, what was it? 120.5 nanometers. Class, is this a blue shift or a red shift? Come on, guys. Blue shift or red shift? I know you can do it.
It's getting shorter, which is blue shift.
That's right. Does that mean motion towards the observer or away from the observer?
Should be toward. It's towards the observer.
Let's calculate the velocity. Oh, by the way, the value that I think it's good to use for the speed of light when doing Doppler shift calculations, it's typical to express the velocities of stars in kilometers per second. The speed of light has a nice easy value of 300,000 kilometers per second, and that's what we're going to use. So we have 300,000 kilometers per second times, let's see, it's 120.5 nanometers minus 121.6 nanometers. We should probably put that in parentheses. Divided by 121.6 nanometers. See if y'all can punch that in without screwing it up. Two sig figs will do.
Is it 9 times 10 to the negative 3?
Did you multiply by 300,000?
Oh no, I didn't do that.
I got negative 2,700.
Units?
Kilometers per second.
Excellent. Christopher, do you know what the negative means?
That it's moving away.
No, that it's moving towards.
Oh, okay.
The idea, Christopher, is when something moves away from you, the observer on Earth, it's a positive increase in distance or in velocity. A negative velocity is towards you because it's decreasing distance, okay? By the way, whoever friended me on Instagram and has the name, where is it? A super evil cat who murders. That's pretty fucking rad. Okay.
That's me.
Thank you, Christopher, for being my friend, a super evil cat who murders. I love it. I love it. Okay. Does everyone have that? Because I need to erase to make some board space here. All right, let's crank out the next three in short order here. Okay, so part B, our observed wavelength was 121.2 nanometers. Let's try this one a little bit different. 121.2 nanometers. Sometimes I like to calculate the Doppler shift, and then it becomes an even easier calculation. So the Doppler shift here is 121.2 nanometers minus 121.6 nanometers, which is negative 0.4 nanometers. Is this a blue shift or a red shift, students?
Blue.
Yeah. And that means towards. Okay. So now we have 300,000 kilometers per second times negative 0.4 nanometers over 121.6 nanometers. That's a little nicer to look at. Why don't you guys punch it up?
Negative 990 kilometers per second.
Good. Okay. Now move on to part C. 121.9 nanometers. Our Doppler shift, 0.6, 0.9 is positive 0.3 nanometers. And it's obviously a red shift, which is motion away. I should have asked you guys to do that, but I'm guessing you would have figured it out correctly. And therefore, our velocity is 300,000 kilometers per second times 0.3 nanometers over 121.6 nanometers. You guys do the honors.
Uh, 740.
Nanometers. I'm sorry, kilometers per second. Okay. And in the spirit of moving quickly, which I know we all like, we'll get right to part D. Part D, 122.9 nanometers. What's the Doppler shift there, guys?
It's
One.
go ahead, Chris. You got it.
1.3.
Red shift or blue shift?
Red.
And let's knock out that velocity real quick. I got 3,200 kilometers per second.
E.
Okay. Cool. That takes care of number 61. Boom. I feel good about this. This means that you guys got to, I'm probably going to make you do a Doppler shift calculation on the exam. So now you've practiced it a bit. It's not complicated. You just take the difference, take the ratio, multiply by 300,000. So you guys are pretty fast today. Can I erase all this? Emily, you cool? All right. I'm erasing. Hey, Emily, are you down to read chapter 15, number 58?
Sure. 1 second. Where do I find chapter 15?
The like previous two homeworks. Let's see here. We're done with
It
this.
doesn't show the previous homeworks. It's only giving me
Oh, because it's hidden from you guys. Right. Right. Okay. I have it here. Okay, I guess I can do the reading today since I didn't put, I'm sorry, that's my bad. I kind of did this last moment. Where are your birds? It's so much quieter in your place, Emily.
yeah, they're being pretty quiet right now. They're all eating.
Oh, okay. That's cool. 58. Sirius A has a luminosity of 26 solar luminosity units. And a temperature of 9,400 Kelvin. What is the radius? Do you guys remember, excuse me. Do you guys know what formula you use, given the luminosity and temperature, to find the radius of a star? I could see having forgotten this one. No. We learned in a previous lecture that there are relationships between a star's luminosity, temperature, and radius. Take a second to see if you can find it while I cough a lot.
I think I have it.
Okay.
L equals R squared times temperature to the fourth.
Yeah, I kind of like, man, I've got a crazy idea. So the actual formula is L is 4 pi R squared times sigma T to the fourth. But that gives me an idea, Christopher.
Oh, no, I have that one too. It's the one below that.
This is in MKS units, right? But I wonder, Christopher, if we did all of this in solar luminosity units, then it should work out that L equals R squared times T to the fourth. It should work provided we use all solar units. And this is in solar luminosity units, but that is not. Would you know how to convert 9,400 Kelvin to solar temperature equivalents?
Divided by the temperature of the sun.
Exactly. And what is the surface temperature of the sun? What is the surface temperature of the sun?
It's 6,000 Kelvin.
Let's use 2 sig figs, 5,800. Christopher, I'm impressed with you, sir, that you were able to deduce that. That makes me very happy. So if you divide those two, what does it come out to be in solar temperature units? Divide them up.
1.6 solar temperature unit thingies.
Okay, so I think I've never actually tried to solve this problem this way, but I think it'll be interesting to see if we can get the right answer. Well, first of all, do you guys know how to solve this equation for R? That's kind of like an algebra thing. Does anyone know how to solve this for R?
You would divide L by T to the fourth and then square root it.
Exactly. So nicely done, Arunsak. Square root of L over T to the fourth. You got algebra skills. So I think what we can do is just do the square root of 26 over 1.6 to the fourth. And I think if we do that, it's going to come out in solar radii. I think. I've never tried this before, so. The correct answer, I think, Sirius is about 2.5 times the radius of the sun. So let's see. Yeah.
I got 2.
Yeah, let's check Wikipedia to see how that agrees. Sirius star. Do. That would be kind of sweet if it worked out like that. The radius is 1.7. Oh, look, they gave us some bogus data. They gave us, see what happens if you plug in 25.4 instead of 26. Well, it's close. What do they have for the temperature here? (99 Kelvin). That's why. Okay, anyways, who cares? We'll go with the book's values. I think we did this right. 2 solar radii is what you would get. By the way, the book, you probably used data from like 5 years ago, and they've probably published papers in the last 5 years that updated better estimates of the luminosity and the temperature of the star. So I think that's why that happened. We'll just go with 2 solar radii because it's a nice, clean, easy number. The real question, which I'm not going to answer because it'll take too many words, but you ought to think about that, is why did it work out that if I got rid of all the constants, why did it end up in solar, that solar units would be the right units? That's something for you to think about. All right, that takes care of question number 2. Looks like a few of you are still writing, so give me a thumbs up when you're better. Okay. Elijah, you cool? All right, okay. Yay. I'm going to erase. Okay. Chapter 16, number 53 is going to be intense. Elijah, I could use your help reading this. I think you have access to it, but I don't know.
So this is chapter 16, right?
Yeah.
Okay, let me see
Open.
if I can find it. Yeah, okay. 53.
I think we need chapter 16, part 3.
Instantly.
Interstellar dust grains, right?
Interstellar dust grains, yeah. Okay.
Hold on a sec. Let me get set up because I'm going to need you to read off the numbers. So this is interstellar dust grains. This is the problem that I didn't have us do last week, but I want us to do it because it talks about a photon propagating through a dust cloud. So before he starts to read, let's all draw a little picture, including you, Elijah. We have a cloud that's roughly spherical, and it's full of tiny spherical dust grains, each of which are made out of carbon or something like that. And then we have a photon of some undeterminate wavelength, like a blue photon, and it's trying to wiggle its way through the cloud without bumping into a grain. We want to calculate the probability that it's going to hit a grain. Okay, take it away, Elijah, when you're ready.
Yeah. All right, so hang on, I gotta zoom in. I can't read. Dark interstellar gas clouds contain so many dust grains that starlight cannot pass through, even though the dust grains are tiny and the spaces between them are quite large by earthly standards. A typical dust grain has a radius of about 10 to the -7th meter. Yeah, and a mass of about 10 to the negative 14th grams. Estimate how many dust particles there are in a cloud containing 1,000. Like M.
Solar mass units.
Yeah. So yeah. So
Or solar
1,000.
masses.
And then of a dusty gas, if 1% of the cloud's mass is in the
Okay,
form
hold on, wait. This is such a big problem. We're just going to focus on one step at a time. So was that all part of A, or were you?
Yeah,
moving-
that was all A.
Oh, wait, okay. So just read all of A once more. Sorry.
Okay. Estimate how many dust particles there are in a cloud containing 1,000 mass, like sun mass things. I already forgot it again. Of dusty
Solar
gas.
masses.
Solar masses. 1,000 solar masses. Yeah. If dusty gas, if 1% of the cloud's mass is in the form of dust grains.
Okay. What I do like about this problem is kind of like that water molecule problem we did last week. It's called a back of the envelope calculation. There's no formula per se. You just have to be kind of smart and think your way through it. We want to find the number of grains. How can I possibly do that? Let's think backwards here.
Wouldn't you want to divide the mass of the cloud by the mass of the grams?
Almost, Christopher, but remember the entire cloud is not all in the form of dust.
Oh, you'd
Only
want to like
1%
take
is dust.
1% of it, right?
Right. So the idea is that the mass of the dust is 1% times the mass of the cloud. So Christopher, I think we can do this in our heads, right? If the mass of the cloud is 1,000 solar masses, then how many solar masses worth of dust do we have?
I think 100.
I think a 100th is 10, right? Because 1 0 2 zeros.
That makes sense, I think.
Well, let's punch into our calculator since we're both confused now, right? If we do 1,000 times 0.01, yeah, 10 solar mass units. Now, Christopher's idea is that the number, the mass of the sun in grams, this is a helpful number to know, is 2 times 10 to the 33 grams. So Christopher's second idea, which was a good idea, is that the number of grains of dust will be 10 solar masses divided by the mass of each grain. But then, Christopher, we should convert this from solar masses to grams. Christopher, why don't you see if you can do this in your head?
That would be 2 times 10 to the 34, yeah?
And now you have to add 14, right?
All right. 48.
That's right. That's 2 times 10 to the 48 grains. We didn't even need a calculator. Sweet. Everyone take a second to get that down before we read the next part. May I erase? Emily, you need a second? Okay, that's fine. Okay. Emily, you good now? All right. Don't forget that number. We're going to need that. Elijah, how about part B?
Yeah. All right. Estimate the total surface area that these grains would cover if you put them side by side. You could assume that the grains are approximately spherical, so each grain covers an area of pi r squared, where r is the grain's radius. State your answer in square light years.
Okay. We're imagining that we're taking all of these spherical dust grains and we're making a kind of chainmail out of them. So, you know, it's Renaissance Fair season after all, and we're going to take those dust grains and we're going to link them all up face on to just see what a target of dust grain chainmail would look like. The surface area of a sphere is 4 pi r squared. But if you just imagine the dust grains as a disk, the photon traveling through the cloud will see each grain as a little disk. So what we want to do is calculate the area of a little dust grain disk, and then we'll multiply it by the number of grains, and that should give us the total area. However, they want it in square light years, correct? So I think that means we have to convert the radius of a dust grain to light years, which is kind of ridiculous, right? That's pretty stupid, but all right, let's go ahead and do that, right? So the radius of a single grain was it 1 × 10⁻⁷ meters? Is that what the given was, Elijah? Did I lose you, buddy?
Oh, no, I was here. I couldn't find the thing. Yeah, the dust grain 10⁻⁷.
So I'm going to put the 1 out front so you guys don't do anything silly like type in 10exp7. All right, so now the conversion from meters to light years is 1 light year is 9.5 × 10⁻15 meters. So go ahead and punch that up for me. This is even worse than measuring the length of a paperclip in miles or something.
I got 1 to the -23.
1 × 10⁻⁻23?
Yeah.
And that's light years for a typical dust grain. So the area of a single disk is pi times 10⁻⁻23 squared. What's 23 times 2?
46.
So that's 3.14 times 10⁻⁻46 square light years. Sorry, I should have put light years in there. I did that right, correct? Yeah. Now we have to multiply that by the total. So the total area is the number of grains times the area of a little disk. Okay, so we're multiplying all these grains times the area of a little disk. What was it, 2 × 10⁻48? Can someone back me up there? I don't know if I remember that correctly. Is it 2 × 10⁻48?
48.
Right. times 3.14 times 10 to the minus 46 square light years. What do you get, guys? 6 times 10, you get about 600, right? 6 times 10 to the 2?
I got 628.
Or 630 square light years. Which is a pretty big freaking area if you think about it. Okay. Let me look around the room here. Is everyone ready for me to erase? Arunsak, you cool? Got some thumbs up from Kaitlyn. Emily, you good? All right, okay. I'm erasing. Told you this problem sucked. Okay, Elijah, hit us with part C.
The leash. Yeah, the leash. Make sure she doesn't run away. Sorry. Part C. PB, stop. Estimate the total surface area of the cloud covers, assuming that its matter density is like that of a typical molecular cloud, about 10 to the negative 21 grams over centimeters cubed. Sorry.
Sure. Grams, we usually say grams per cubic centimeter, but the way you said it was okay too.
I have cave brain today. I can't read.
I was saying some funny words earlier myself, so I get it.
Do you want the hint or just skip it?
Hold on, I'm gonna sneeze. Thank you. Can you just read me the whole thing again? Because I really confused myself.
Sorry. Estimate the total surface area of the cloud covers, assuming that its matter density is like that of a typical molecular cloud, about 10 to the negative 21, the gram cubic meters again, or cubic centimeters. And then state your answer in square light years.
Okay. So I think we're going to imagine the cloud is like a big disk, right? Like if we slice through this cloud, then we're going to see a big disk of pi times the radius squared. So we're going to have to do something kind of nutty here. Remember that the cloud has a mass of 1,000 solar mass units. We're going to use the density to find the volume of the cloud. Then we use the volume of the cloud to find the radius of the cloud. Then we use the radius of the cloud to find the surface area of the cloud. It's going to be a bit wacky, but hang on to your shorts there. Okay, so we know that density is mass divided by volume. We know that the volume of a sphere, I'm going to assume it's a spherical cloud, is mass over 4/3 pi r cubed. If I solve this for radius, hey, Arunsak, are you good enough to solve this in one shot in your head? Can you solve this for radius? You can't do it? I'll show you how you do it. Ready? The 3 should actually be up here next to the m. Four goes up, 3 goes down, pi goes up, mass goes, wait, no, sorry, let's try that again. Radius goes up, density goes down, and then we take the cube root. So radius will equal the cubed root of 3m over 4 pi times the density. Okay, so that gives us the cubed root of 3 times 1,000 solar masses times 2 times 10 to the 33 grams per solar mass over 4 times pi times 1 times 10 to the negative 21 grams per cubic centimeter. See if you guys can punch all that up or try to do it in your head. We could say 3 and pi cancel out. That's 2 times 10 to the 36, 1/4 times, actually just plug into your calculator. I don't feel like trying to do that. The cube root is going to mess me up here.
I got 3.6 times 10 to the 18th.
It's not what I got.
Hmm.
I got close. I got 7.8 times 10 to the 18th. Wait, what does the rest of the class get though? We need a second opinion here, or a third opinion. What do you guys get?
Oh, I see where I went wrong. Accidentally multiplied 3 times 100.
Oh, well, I get 7.8 times 10 to the 18. Did anyone else get that? No? What'd you get, Stacy? Can you read it?
What did you get, Professor?
7.8 times 10 to the 18.
I did something wrong. I got 4.77.
Can we do it together?
Yeah, all right. Watch my moves. 3 times 1,000 times 2 exp33 divide by 4 divide by pi divide by 1 exp21 negative, then equals, then shift cube root. 7.8 times 10 to the 18. What are my units? I'm going to have to erase up here.
Is it solar mass per centimeter cubed?
Solar mass is clearly canceled out.
Centimeters cubed.
But it's the cube root of centimeters cubed.
Centimeters.
Exactly. You've got to distribute the cube root. Now, they want us to calculate the surface area, the disk area of the cloud in square light years. So let's again convert this from centimeters to meters and from meters to light years. How many centimeters are in a meter, class? If you don't know the answer to this, I want to die. How many centimeters are in a meter?
1,000.
3.
That's it. All right. So how many centimeters? Centi. No, I'm just kidding. I should not make those jokes. How many centi?
100.
Oh, yes, sorry. Someone said 1,000 before, so all right.
It was me.
But you corrected yourself, so we're cool now. And 1 light year is 9.5 times 10 to the 15 meters. Okay. So what's my radius then?
8.2 light years.
Nice. And now we'll calculate the surface area of the cloud. We'll imagine it's like a disk. Pi times 8.2 light years squared. And just to save you a little bit of time, I get 210 square light years. And if you can believe it, there's even a part D.
I got 211.
Oh, did you now?
Mhm.
I just rounded it to 2 sig figs. Right? The reason why is because I didn't round, I used the 8.2 something something. It doesn't really matter. Just 2 sig figs, Christopher. Okay. Elijah, what's part D ask?
Based on your answers to parts B and C, what do you think the chances are that a photon passing through the cloud will hit a dust grain?
Okay, now I want you guys to remember what we calculated. This is the surface area of the whole cloud, but the surface area of all the grains, what was it again from part B? What was the answer to part B?
630 light years squared.
Doesn't that seem weird? Christopher, if the dust grains are inside the cloud, how can the total area of the grains exceed the total area of the cloud? Doesn't that seem kind of messed up to you? How can the total area of the grains be greater than the area of the cloud if the cloud contains the grains? Does anyone understand what's going on there? We treated the cloud like a cross-sectional disk. We sliced it in half, and we imagined that the photon was going through there. But if you take all the grains forward and back and you collapse them and compare them against that disk, since the grains are distributed deep into the cloud, they end up having more target area than the cloud itself. Therefore, in part D, we say the probability that a photon will hit one of the grains is the ratio of the area of the grains to the area of the cloud. It's the area of the grains over the area of the cloud, which is 630 square light years over 210 square light years Holy shit. Exactly 3. That was cool. What is the meaning of 3? Can you tell me what a probability of 3 means?
1 out of every 3. No.
That would be 33%, Kaitlyn. What is the probability that a photon will hit a dust grain?
3 times?
Not 3. Well, kind of. Jesus, guys, do probability right. What is 3 represented as a probability?
Would it just be 3%?
Sorry, Elijah, I can't hear you because of the dishwasher.
Would it just be 3%?
No, 3 is not 3%. Is 1 1%?
It's 300%. So
what are
it's there's a 300% chance it's gonna hit the cloud.
not the cloud, the grains?
The grains, yeah, the grains. That's what I meant.
Or what else does that mean though? Like Arunsak, if it's 100% chance that a photon hits a grain, then a photon hits a grain. What does
It's
it mean?
gonna hit 3 grains.
That's right. It will stop off at least 3
Yeah.
grains on its journey to the cloud. This is what creates the reflection nebulae. The blue photons end up having to hit a few grains on their way through even a very low density cloud because there's so many bloody dust grains. And that, my friends, is how we get a reflection nebula. Okay, we got one more prob left. Make sure you guys got all that down. Emily, give me the thummy uppy when you're ready to go. Okay, everyone else good? All right, we're almost done, guys. We're almost done. I give you 10 points for that question. Last up is us using the Jeans mass law, the temperature for, this is a really easy problem. Chapter 16, number 54 is using the so-called Jeans mass, which is the minimum mass for star formation. Okay, so if we share screen here, 54, an isolated star-forming cloud. Isolated molecular clouds can have a temperature as low as 10 Kelvin. Let's write that down. And a particle density as great as 100,000 particles per cubic centimeter. What minimum mass does such a cloud need to form a star? So the number density here is 100,000. Remember how we write this? We can write particles per cubic centimeter as centimeters to the -3. The Jeans mass formula tells us that the mass the cloud must have to form a star is greater than 18 times the mass of the sun times the square root of T cubed over the number density. So we'll put these things in here. The mass of the cloud is 18 solar mass units times 10 Kelvin cubed over 100,000. You guys had some trouble with this last time, so see if you can punch that.
.18.
Not what I got. How did you type in this?
I
Please
just
tell
put
me-
that down as 10.
Huh?
I just put it in as 10. I forgot the cube.
Ah, that's what went wrong. Anyone else?
0.18.
Say that, Kate.
0.18.
I got something. You're off by a factor of 10. Did you type 10 EXP3 there? No. Did you cube it? You forgot to cube it.
Yeah, I forgot to cube it.
All right, so you
I
did
got 1.8. No.
Yeah, cube it again. You should get
0.42.
no. Here. 10 shift cube is 1,000. divide by 100,000. You get 100th. Square root that to get a 10th. Then times 18 to get 1.8 solar mass units. Please verify that you guys can do that. Can you guys tell me what spectral type that would be? Why would I expect you to be able to guess the spectral type? What's the spectral type of a sun-like star?
Emission.
No. First of all,
It's,
stars. Huh?
G, right?
Thank you. Christopher understands me. The sun is a G-type star. What's the mnemonic device to remember the spectral types of stars?
Something gentlemen kiss me. I can't
Oh,
remember that.
Oh, be a fine girl, kiss me. That's what it is. So what's before G?
Oh,
The same thing you're going to get on your final exam, an F. Okay. Okay. Bad joke. Bad joke. Just kidding. Okay. Unless you fucking learn, oh, be a fine girl, kiss me. You guys need to know that, okay? Oh, okay. Oh, be a flavorful God. A flavorful God. Okay, I like it. I like it. I'll make sure that oh, a favorful God and kill me before the exam. Okay, yeah, right. Well, you've done it. You wasted another afternoon learning about stars with me. Okay. That was a lot of fun. And I hope you guys have a good election. I hope we all have a good election. We'll see. Anyways, I'm gonna stop the recording now before I say something stupid.